Here is another example of a limiting reactant percent yield type problem. This reaction is used to obtain iron from iron ore. Fe2O3 is reacted with carbon monoxide to produce iron and carbon dioxide. The reaction of 185 grams of the iron oxide with 95.3 grams of carbon monoxide results in 87.4 grams of iron. Find the limiting reactant, theoretical yield, and percent yield. This problem is a little different from the previous problem, isn't it? So, before we panic, because I know that's what some of you do, it's okay. You need to read the Hitchhiker's Guide to the Galaxy. Big friendly letters on the cover, it says, don't panic. Panicking doesn't help anything. Let's take these numbers and sort them out. We'll use the balanced chemical equation to help us organize this information. So 185 grams of the iron oxide. So we're going to write that underneath the formula. And 95.3 grams of carbon monoxide and 87.4 grams of iron. It's not a very good 7. My 7s lately have been looking like 2s. I don't know why. Those are the numbers they gave us. What are they asking us for? Well, they want to know the limiting reactant, the theoretical yield, and the percent yield. How do we find the limiting reactant? We do those two equations, right? And then we find the smallest amount of product. That's the theoretical yield. And we look back and we see what reactant gave us the smallest amount of product. That's the limiting reactant. And how do we do percent yield? Percent yield is the actual yield divided by the theoretical yield times 100%. So if everything worked perfectly, you'd get 100%, right? But stuff doesn't work perfectly. It never does. So your yield is generally going to be less than 100%. To find that, we need the actual and the theoretical yield. The actual yield has to be given to you. It can't be calculated. It's an experimental thing. When we do a lab, you're measuring the actual yield, okay? But in a problem like this, you're not doing an experiment. They have to give it to you. So that means that one of those numbers is the actual yield. So they gave you an amount of iron, right? That's going to be the actual yield. This problem can be confusing because they gave you 3 masses and they didn't really label them at all. They just are giving you 3 masses. Because what we're used to, or we're getting used to, is having masses of 2 reactants, and then they're asking us to find the mass of the product. And so it might throw you off that they're giving you the mass of the product. But what they're giving you is the actual yield, and we still need to calculate the theoretical yield. Everybody with me on that? So calculating theoretical yield, we're going to follow that map, grams to moles to grams. So we'll start with the Fe2O3. We've got 185 grams of Fe2O3. We're going to convert that to moles of Fe2O3. And then to moles of iron. And then to grams of iron. Grams to moles to grams. The units guide us. They tell us what to do. We take the previous unit and put it in the denominator because we want those to cancel out. We get all of our units in place before we go throwing numbers in there. So all of our units are in there. The middle term, mole to mole, is the easy one. The numbers come from the equation. In front of Fe, we have a 2, right, in the equation. And in front of Fe2O3, there's nothing, which is an implied 1. Now, I was talking to some students yesterday, and this is a common problem that I'd kind of forgotten about. That coefficient 2, the only place you use it is in the mole ratio. That doesn't come over here into the molar mass. So when we find the molar mass of iron, we're not looking at coefficients, we're only looking at the formula. The formula is Fe. So we find it on the periodic table, 55.85. 55.85. We don't multiply that by 2 because there's a 2 in front of Fe. We want to know how much each mole of Fe weighs. We're finding the mass of 1 mole. The molar mass of something is the same no matter what sort of a reaction it's in or being produced by. That 2 pertains only to this particular reaction. If you do a different reaction, there may not be a 2 in front of the iron. The molar masses are always the same. Okay, so it's a common mistake that students make, and I want to warn you about it so that you can avoid making the mistake. So then for the Fe2O3, we need 2 times the mass of iron, which we just figured out was 55.85. Yeah. And 3 times the mass of oxygen. I know I forgot something. Two times 55.85 plus 3 times 16, 159.7. That mass of iron 3 oxide is equal to 1 mole of it. It's the mass of 1 mole. So we put that in here, 159.7. And now we can do our calculation. 185 divided by 159.7 times 2 times 55.85. How many significant figures should that answer have? 3. Our answer, the mass we were given had 3, so we can round this. 129 grams of iron. And we're out of space, aren't we? Completely out of space. So then we get creative. And we create some space by covering up some things we don't need to look at. So that's the amount of iron we could make if we use up all the iron oxide. Then we have to do another very similar calculation using the carbon monoxide. So 95.3 grams of carbon monoxide. Again, grams to moles to moles to grams. So we go to moles of carbon monoxide to moles of iron to grams of iron. Grams to moles to moles to grams. And we put the previous unit in the bottom because we want them to cancel out. That's a capital O. We get all the units in first. All the units. Then put the numbers in. So the middle term is the easy one because we just get it out of the equation. In front of the iron is the number 2. So we put a 2 here. And in front of CO is the number 3. That's the only place you can use those coefficients. Don't do them anywhere else. So for moles of carbon monoxide to grams of carbon monoxide, we need the molar mass of carbon monoxide. So we've got carbon is 12.01 and oxygen is 16.00, just one of each of them, and that comes out to be 28.01. So that's grams of carbon monoxide is equal to 1 mole. Do not multiply it by 3. We want to know how much 1 mole weighs. So 28.01 goes in here. And then this last term is the same as the one below. The mass of iron is still the same, 55.85. So that's like your little bonus there. So 95.3 divided by 28.01 times 2 divided by 3 times 55.85, and I get 127 when I round it. Anybody else get that number? Those numbers are really close, aren't they? 127 and 129. We haven't seen numbers that have come that close. So these amounts are actually pretty close to right on, but 127 is smaller than 129. So this is the theoretical yield. So that's the answer to, there's actually three answers we need to give here. That is one of the answers, that's the theoretical yield. What is the limiting reactant? The CO. So what we're doing is we're finding the smallest amount of product, and then you just look back and see, well, which reactant did I start with there? And that is my limiting reactant. So carbon monoxide, that's my limiting reactant. But they've asked us for one more thing, percent yield. The percent yield is the actual yield divided by the theoretical yield. We just calculated the theoretical yield. Now we can use this equation up on top. They gave us the actual yield of 87.4 grams. And we're going to divide by the theoretical yield that we just calculated and multiply by 100, and there's no room for the answer. 87.4 divided by 127 times 100. How many sig figs should this answer have? It should also have 3. So that's going to round to 68.8. Now, if this was your paper, I would have a hard time seeing that. So then you want to put a box around it. This is the percent yield. My eye is drawn to boxes. So you might look at that and say, well, that's a sloppy, messy paper. Well, you know, it could be better, but we can read it. All the units are there. The equations are laid out. The answers are boxed. In my mind, that is acceptable. That's definitely acceptable. Any questions about a problem like that? Yes?
What about the other product, CO2?
What about the other product, CO2? Well, the other product is also made. In this question, we don't care. Could we calculate how much is made? Yeah, we could, if we wanted to. But why would we want to, right? Just for fun. You're like, this isn't fun. I think it's fun. Yeah, we could calculate that. In fact, I think there's one of the Mastering Chemistry homework problems gives you a mass of a reactant, and there's actually 3 products, and then it wants you to calculate the mass of each product, and then it gives you a mass of the other reactant and asks you to do basically the same thing. Like, oh my goodness, that's a lot of work. Well, it is and it isn't, because a lot of those equations you can recycle. You can just, you know, if you're doing mass of iron oxide, and you've already calculated mass of iron, and now you need to do mass of carbon dioxide. You just need to change those last two terms, and you're good. Okay? Any other questions?